So as you've noticed, I skipped ahead a little bit to page 27. Not that the other pages weren't important, but they're mostly on our last unit on area, volume, and volumes of revolution and volumes with known cross sections. So on page 27 on the bottom, I'm resuming with if we were doing approximating area with slices. So the area we're approximating is the actual area underneath of this curve. So if we just have a table of values here, it's given right here, then if we wanted to estimate using trapezoids or the trapezoidal rule, that's where we would average the heights times or average the bases times the height. So for the first section here, that would be 2 times the average of 10 and 13. Plus then the next one would be 3, the difference between 2 and 5, times the average of 13 and 11. And then the last one would be 5 times the average of 11 and 15. Now if you had equal subdivisions, then you could factor out that height, if you will. But since they are not equal subdivisions, we can't factor that out. And of course, you could do the value for it. If this was a free response problem, you can leave it exactly as that. And you can check the answer with the Calc Bible answer key. If we're doing left endpoint, I'll change colors here. Then what that would do is it would make a rectangle here, here, and then here. And we would find the sum of those rectangles, so that would be same widths of each subinterval, but then I would use 10. Then for the next one, I would use 13. Oops, putting this in the wrong spot. And then for the next one, I would use 11. So let me move that. Only difference for right endpoint is now I would be using these portions, so the values on the right, still the same width. Then I would use these values. And once again, if it was free response, you could leave it as this. For the first fundamental theorem of calculus, that's essentially your f of b minus f of a. I'm going to skip that, but depending on which textbook, second fundamental theorem or first fundamental theorem, part 1 or part 2, bottom line is if you're doing a derivative of an integral, you can essentially cancel each other out. In other words, for this first example, if it's derivative with respect to x and we have an x up here and a constant on the bottom, I can really just plug that x in, get x to the third. There would be a longer way of thinking of it. This, you could do the antiderivative, plug the x in, plug the 0 in, then do the derivative term by term, but this is the easier shortcut. Thing to be careful of is if you have that x on the bottom, that's essentially going to be filled in, but then also a negative, and the chain rule would apply. In other words, it would be negative x squared to the third, and chain rule would apply. Same idea in example 3, the x squared would go in, and the x would go in, and also chain rule would apply for when the x squared goes in.